Good afternoon. My name is Yael Gonzalez, and this is my implementation of the Dijkstra algorithm for the project 3, the shortest path routing problem. And the problem that we're going to be solving is going to be the one from the guidelines of the project, where we have a graph, different nodes that represent networks in a given state, New York, New York, and so on. And we have to find three shortest paths for the examples that we see right here at the bottom. We start in the notebook with the implementation, and as a small side note, a really useful tool was this library, the network analysis in Python library, because it gives a lot of information, right? Not only documentation, but overall knowledge of how everything works, and specifically about the algorithm. Even it gives a sample, and more than that, we also have certain functions that we can use as inspiration. For example, Dijkstra path length was of heavy inspiration, and it uses the graph, the source and the target as input, and similar to what we implemented. So going back to our notebook, I'm going to go over a simple explanation of the algorithm. As I said, the input is the graph, the source and destination. It returns the path, the total distance, and some metrics. The start time is a metric. We start with our distances, right? This is our distance so far to a given node. We set it to an infinite, so we have a really, really big number. And this is because if we find a shorter, like a smaller amount or a smaller distance, then we can easily replace it. We have our previous. This is a dictionary of nodes, and it's going to be used for reconstructing the path, right? We're going to go, once we reach our destination node, we go backwards, building the path again. And that's what we use previous for. We set the distance to the source 0, because obviously from source to source, it's 0, and we create our priority queue. And here's the main algorithm where we basically pop an element from our priority queue, and we check the neighbors, and we start finding, the current distance that we have, plus the way to get to a given neighbor. And if that distance is less than the previous distance that we had for that neighbor, then we have found a shorter path for that specific neighbor, right? So it's a more optimal path so far in the algorithm. So we update that information, right? We say that in our distances to the neighbor, we find that new distance, and our previous from that neighbor is the current node that we are in. And now we push it to the priority queue, and we repeat this process over and over again until we find our shortest path. Finally, once we're out, or in this scenario, if no distance is found, we go over everything and there's no shortest distance, so there's no path to get to the node, then we have this part. It says, hey, if my distances are still infinite, return none, no path was found. But if we do find a path, then, as I said, we go backwards, right? We use our previous dictionary that we use, and we start going backward from our destination all the way back to the start. And finally, we reverse it, because that means we're going to have our path from finish to start. We reverse it, now we have a start to finish. We store some of the metrics that it takes as execution time, path length, so on and so on. And we return the path that we found, the total distance, and the metrics. Here we have our network visualization. Let me already run that. Our network visualization is an optional part, but I find it really useful whenever I deal with algorithms. Same thing for AI algorithms, where we're gonna map our graph so we can see it similar to the image in the guidelines. It's pretty straightforward. It uses positions. We're gonna go over that later, but it uses positions to place the node, and it uses our neighbors to draw maps. So we have a node, we find the neighbors, we draw lines or weights to it, and we get the weights from our network dictionary that we're gonna go over. So this is our inputs. The network definition of our text. This is what I was talking about. We have our network where we have a given node and its neighbors and the weight to that neighbor. So we have WA to CA1 is 1050, CA2 is 1500, and IL is 2400. And we do this for every node. Then we have our positions, and this again is for the visualization. The visualization does not affect the algorithm whatsoever. It's for the user. But the position just tells it in the graph that we're gonna display where to put each node, right? And we're gonna do that similarly to the image of the guidelines. And these are text cases, are the examples that are showing the guidelines that we have to find. Finally, we have the part where we run the algorithm. This is the execution. We go through every test case. We call our shortest path function for that given network source and destination. And then we draw our network so we can see the path that we found, and then we display our metrics. And if we run this cell, we can see the entire execution. So our first algorithm is New York to CA2. It shows the path that it found visually, and we have a similar reconstruction of the graph of the guidelines, and we have some metrics, right? The total cost was 3,900. It visited 50 nodes, 41 attribute sections. The path is built of 4 nodes, as we can see in New York, DC, Texas, and CA2. And the hub count is 3 links. It has 3 edges. Finally, we have the execution time. That is going to be super short because it's a fairly small network graph. And we can see the same information for every given exercise. So we have our WA to GA. We have finally our CA1, 2, and J. So California 1 to New Jersey, I'm guessing. And we see the path that it found. And we see more metrics. It's fairly short execution time because it's really easy to traverse the entire network. And that will be all for my walkthrough of my implementation for the Dijkstra algorithm.